Welcome to Daily Papers, the podcast where we break down fascinating new research into bite-sized conversations.
Today, we're diving into a really cool question about artificial intelligence. How does an AI learn to plan ahead? It seems simple, but it turns out there's a surprising twist. We usually think of AIs in two main categories.
Right. On one hand, you have your model-based AIs. You can think of these as the meticulous planners. Before they make a move in a game, they build an internal map or a model of their world. They use this map to simulate different futures. If I go left, what happens? If I push this block, where will it end up? It's like a chess grandmaster thinking 10 moves ahead.
Exactly. And on the other hand, you have model-free AIs. These are the reactive ones. They don't build a complex internal map. Instead, they learn a direct, almost instinctual link between what they see and what they should do. If they see a certain board state, they just know the best action to take without thinking through all the consequences. It's more like a reflex.
So, the traditional wisdom has always been that planning is strictly for the model-based AIs, the ones with the maps. The model-free AIs are just supposed to react. But then, researchers started noticing something weird.
They did. They found that some of these purely reactive, model-free AIs were actually planning. They were testing an AI on the puzzle game Sokoban, the one where you have to push boxes onto target squares. And they noticed that if they gave the AI a little extra time to compute before it made a move, its performance got dramatically better.
And giving an AI extra thinking time and seeing it improve is a classic sign of planning. It suggests the AI is using that extra time to do something more than just react. It's deliberating, refining its strategy. So the big question, and the question this paper tackles, is how? How can an AI that wasn't built to plan suddenly learn to do it all on its own?
The paper, titled Planning as Emergent Behavior in Reinforcement Learning with Relational Hidden States, suggests the secret isn't in the learning algorithm, but in the AI's fundamental architecture, basically its brain structure.
The key concept they propose is something called relational hidden states. Let's break that down. Hidden states are basically the internal thoughts or memory of the neural network. And relational means these thoughts aren't just one big jumble. They're organized into a network where different thought cells can communicate with each other by passing messages.
But here's the most important piece of the puzzle, the ingredient they call anchoring or binding. Imagine you're trying to navigate a city. You have a mental map where each landmark has a specific, fixed location. The Eiffel Tower is always in one spot in your mental map. Buckingham Palace is always in another.
This paper argues that for an AI to learn to plan, it needs a similar internal setup. Each part of its environment, like every single square on the Sokoban game board, needs to be permanently linked or anchored to one specific thought cell in its internal network. The top left square of the game board always communicates with neuron A. The square next to it always communicates with neuron B, and so on, a fixed, stable, one-to-one mapping.
So, to test this idea, they set up a kind of AI showdown, all playing Sokoban. First up was an AI that had this anchoring built in. Each square on the board was locked to a specific internal cell. But the AI didn't know how the squares were related. It had to learn from scratch the rules of the world, that you can't move through walls, that you can move from this square to that one.
And what happened, it worked. By trying to maximize its reward, the AI used its anchored network to learn the layout of the game board. It essentially built its own internal map, and based on that map, it started to plan its moves. It showed that classic signature: give it more thinking time and it plays better.
Now for the crucial part of the experiment, the control agent. They built another AI that also had a network of thought cells that could pass messages, but with one key difference. There was no anchoring. The cells were free slots. On every turn, they had to figure out for themselves which part of the board to pay attention to.
And the result was a total failure. Without that stable one-to-one mapping between the world and its internal brain, the AI couldn't form a coherent map. Its internal representation was a jumbled mess that changed from moment to moment. And because it couldn't build a map, it never learned to plan. Its performance was flat. Giving it more thinking time did nothing.
It's such a clear result. The ability to plan didn't just come from learning to get rewards. It emerged because the AI was given a specific architectural advantage, a stable, anchored structure on which it could build a model of the world. It's like you can't draw a map on a piece of paper that's constantly shuffling itself. You need a fixed canvas.
So, to sum it up, it seems that the line between reactive AIs and planning AIs is much blurrier than we thought. An AI can learn to plan, to think ahead, without being explicitly programmed to do so, as long as its internal architecture provides a stable foundation for representing the world.
And the paper ends on a really tantalizing thought. This mechanism could be a clue to how our own brains work. Cognitive scientists often describe parts of our brain, like the hippocampus, as a sort of relational map that binds our experiences together.
So maybe our ability to plan isn't some magical, high-level process, but an emergent property that arises from our brain's fundamental structure, which gives us this anchored, relational way of seeing the world. A really fascinating idea that bridges artificial intelligence and neuroscience.
And that's our paper for today. Thanks for tuning in to Daily Papers.